Well, I'll give him that. They did use enough bubble wrap. But, yeah, not like, and that's how it arrived. I didn't do that, but almost there. Well, it's almost out. And the CRT is not cracked, at least not on this side, so that's a good sign. I give them a C+ on packaging so far. Alright, so finally got this thing up the stairs and unboxed. And it looks to be visually and physically in pretty good shape. But before I start, going into a bit more of an investigation of this thing, just wanted to go over what this thing is for those of you who aren't familiar. So this is a Tektronix 576 curve tracer. Now these were made back in the late 60s, early 70s. Not sure how long they were made for, and they're not made anymore, but um, you know, I have always been fascinated with these as soon as I had heard of their existence. I saw a couple of my favorite YouTube engineers using them and just thought they were really, really cool pieces of equipment. So I really wanted to get my hands on one, and I, you know, finally found one listed on eBay for parts or repair for a reasonable price, or at least what I thought was a reasonable price, and I just went for it. And so these things, um, they have a few different applications, but basically what they can do is they can test semiconductors, so diodes, transistors, triacs, uh, thyristors, any semiconductor that they can test and produce IV curves, so current versus voltage traces, which can provide a lot of characteristics on that semiconductor. They're great for, um, if you are looking for a suitable alternative transistor, you can't find the original, it's discontinued, and you need to find a suitable modern alternative. They're great for comparing those. Um, and they're just great educational tools as well. So I really wanted to get my hands on one, and I'm ecstatic that I was able to get one. But I knew that this was probably going to be a restoration project of some kind. Um, Now, the seller did say that the CRT was working. He showed me some pictures of it on, so that was one of the reasons why I jumped on this guy, because I've heard that the high voltage transformer can be an issue with these. So that, I'm going to obviously investigate further, but that appears to be working. But so that's a good sign. The rest of it, as far as I am aware, is mainly discrete components, meaning that there's no microcontroller, microprocessor. So the rest of it should be theoretically repairable, because there's no proprietary components in there. Well, in the sense that are programmed, which can be a hurdle for doing repairs. So that's also another reason why I wanted to grab one of these and give it a restoration a shot. So let's take a closer look at these. I've already unscrewed the side panels, and we're just going to take those off and just take a closer look. Okay, so I've got the side panels off, and let's just do a quick physical inspection. So a couple of things that I noticed right off the bat. So this is the max peak voltage knob, and you can set the collector voltage from this knob. Sorry, my camera's not focusing here, but okay. But one thing that you can also do with this is you can set the peak power watts, which changes the series resistor values. This piece, which sets that, has separated from the push-pull knob. Okay, so we'll have to glue that back in place once we find the correct orientation. So that's one thing I noticed. Another thing, well, these things can also come with accessories. So this is how it comes standard. This whole apparatus here is called the standard test fixture. Um, there's also these fixtures that will plug into these inputs for testing transistors or FETs, diodes, all different kinds of test fixtures. And for my research, these can be just as expensive as the instrument itself. We can get around this just by plugging in some test leads to do some testing. So they're not critical to running the instrument, but it does just make it safer, especially when you're testing components at higher voltages. So that did not come with it. And another thing, speaking of testing at higher voltages, is there is a plastic cover that goes over top of this when you have it at voltages greater than 15 volts. And in fact, it will not work at higher voltages without that. And there's a little button that is actually stuck in the depressed position there that I would assume would get triggered when you put the cover over it and disable the high voltage interlock. So that is also something I noticed. Another thing, it looks like the cover for this switch, which toggles between the left and right test fixtures, or in the off position, so you don't have these being live. The cover on this is broke. Not the switch itself, it's just the plastic piece, and actually it was like half there and it came off, so not a huge deal, but that's missing. Let's see. These gang switches down here for setting some of the step generator parameters, they don't stay depressed like this normal switch. So might have some issues here. Let's see. But yeah, that seems to be all that I can find, like as far as physical issues. Pretty not bad. Because from what I can tell, these knobs, one, they're hard to find, and two, I've seen other people restore these. They are prone to breaking. Another thing where they'll break, and I should preface, I've never worked on one of these before. I've never used one before, but this is just what I've found researching them. So a lot of these switches or pots, knobs, they will run the length of the instrument, and they are usually connected to the actual switch via these couplers. I've seen these break. So, someone who's selling one of these who may not be familiar with them will think the whole instrument is non-functional, and it could just be due to one of these quick couplers being bad. Doesn't look like that is the case with this one. So you can see all of the quick couplers are, in place. See? Which is a good. And that's a relatively easy fix anyway. You can get these types of couplers in different sizes, from Granger or McMaster Carr. So that would have been a relatively easy fix. But yeah, so that's a good. These are some of the circuit boards for the instrument. I mean, look at this. This is just incredible. Visually, all look to be in great shape. Not seeing any blown components. Obviously, that doesn't mean it's working, but, nothing out, nothing like that is, conspicuous. So, this is the low voltage regulator board. These caps might be suspect. We'll have to test those. But that's where you can test the power supply voltages. And you can kind of see back there where it says C791. Those are some of the big caps for the power supply. Those also might be bad. Those might need to be replaced. But yeah, I mean, visually this thing looks pretty good. Okay, no dents or anything like that. Really made out pretty well here so far. Let's take a look at the other side. And this is the CRT for the screen, the display. This big switch that we were just looking at is the collector supply switch, so that's how you'll be able to change the collector supply voltages. There's actually normally a big cover here that I removed, just for protection purposes, a plastic cover, you know, so that was there. But yeah, looks in really great shape. Why don't we plug it in and see what else we can find. Alright, so I've got it plugged in here, and actually just one other thing I wanted to point out is it has this selector switch for operating in either at 120 or 240 volts, and even has low, middle, high, so you have a lot of adjustment here based on what your mains voltage is at, which is pretty neat. But we've got it set to, you know, the middle position at about 120 volts, which is what we get here in the US, and it's at 60 hertz. But just thought that was pretty neat. But yeah, let's power this guy up. I also did test the fuses to make sure they were in good shape and none of them are blown. So yeah, let's power this guy on, see what happens. Okay. So yeah, you can see we've got a trace on the screen, which is neat. Yeah. Okay. Very cool. Yep, at the brightness. Okay. Nice. All right. So that's really good sign. So yeah, what I'm gonna have to do is I'm gonna have to open up the service manual and see if there's like a you know, first time operating procedure, because I have no idea how to use this thing, and kind of walk myself through that. And one thing that I did notice is again, I mentioned this before, but got to find a way to disable that that safety the high voltage interlock switch. So I'm gonna have to look into that. I'll probably remove this test fixture and take a closer look there. But yeah, I'm gonna open up the service manual and take a closer look, just to see how to use this thing. But all right. All right, so I have here the standard text fixture from the curve tracer. I was actually looking into disabling the high voltage safety interlock, because obviously this one didn't come with this protective box that you can put over the test inputs. So when you're switching from 15 volts to 75 volts, the interlock is automatically engaged. And the yellow light will come on by putting this protective box over this this red light will come on. I don't have this protective box. It seems like there's some kind of switch that senses when the lid is over top of this, that then this light will engage, and then, you know, it will be, you'll get voltage um, from the collector after that, but don't have that capability. So I was looking into disable it. The service manual shows you how, and I was just not this is not, I don't think this is where you would disable the interlock, but anyway, I was looking in here, something caught my eye, and I'm gonna try and see if you guys can see that. But this resistor here on the terminal selector switch is just blown in half. Yep. So yeah, that looks like it could be a 220 ohm resistor, unless that black band is charring. But it literally just looks like it's snapped right in half. So yep. So gonna replace that with a suitable alternative. But yeah, just wanted to show you guys that. This is the first thing that I found visually that I could tell what was wrong with it. So yeah. Alright, so I've moved on to trying to troubleshoot this high voltage interlock issue that you know, that's going on with this curve tracer. So I just wanted to go over a little bit of how this thing works. So you have 4 separate ranges for the collector voltage that you're going to apply to the test fixture. There's 15 volts, 75 volts, 300 volts, and 1500 volts. It has a lot of power, which is why these things are pretty sought after and makes them kind of unique compared to other things on the market. So, but anyway, 15 volts, the relay is automatically on applying voltage, but as soon as you get up to 75, the safety interlock kicks in and disables the voltage to the collector, and then a yellow light will come on next to that green power light, and the only way you can enable it is if you well, let me first start by saying these usually have a plastic safety box that will cover the test fixture, and so until you cover this fixture with that plastic box, you won't be able to disable the safety interlock. And then once you do that, the yellow light will come off, and then this red light will come on, indicating that this is live with some high voltage. And the way that that works originally is there is a little board, this guy, which I've altered, by the way, I'll go over that in a second, is connected underneath there, and so this guy is the switch that is soldered into this board originally, and it'll sit up like this, and there's 2 screws where it'll attach to the top, and there must be, I don't have the plastic box, but there must be a little, you know, nub or something of that box that will touch that switch and trigger it. So I wanted to figure out how I can bypass this. So this guy's pretty unique. I haven't ever seen one of these before. It kind of threw me off. And in fact, initially, this guy was stuck already in the closed position, which was already an indication that this guy must be faulty, because I was still disabling the high voltage for me. So yeah, I did put some contact cleaner on it to get it to open and close, but yeah. So one thing I also noticed about this guy is I don't know when, um, how long these were in service for, and someone can maybe chime in the comments. That'd be awesome. But I see copyrighted 1968 all over the thing. Um, a lot of older looking components, maybe from like this early 70s as far as the circuit boards. I haven't taken a closer look and actually looked at any to see if there's any date codes on any chips, but just looking at it visually. But this guy says copyright 1985 on it, which I thought was interesting. And I know that these can be sold separately on eBay. And so maybe this isn't the original? I'm not sure. Um, but I couldn't really find anything also in the service manual for this as far as a schematic. Maybe it's just not noted or, but maybe the original had a different safety interlock. Maybe I'm wrong. I don't know, but just something I wanted to note. I'm not a collector, I didn't buy this to, have it completely original. I bought it so I could do some cool electronic shit with it. So, just a note that I thought was interesting. But anyway, um yeah, so I needed to figure out a way to bypass it. Now, the service manual does um give you, at least the service manual I found online, um it does provide a way to disable the safety interlock. But as far as I can tell, it does involve getting in to the internals of the instrument. You got to get to this connector J300, and it's buried under a lot of stuff. You'd have to remove a lot of components, um, a lot of boards. It just doesn't seem all that easy to get to, and I would like to avoid doing that if possible. Um, who knows? I might have to get in there anyway. There still seems like there's some other issues with it, but anyway, I wanted to avoid doing that. So figured I could maybe find a way to rig this switch in the open, or I mean closed position. So yeah, well, I needed to figure out what the hell this thing does. Um, so I was able to find a data sheet for this guy. Um, uh, Let me pull that up here. Every time I shoot one of these videos, okay. Sorry about this. All right, so yeah, I was able to find, believe it or not, the data sheet for this component. And it is a slotted optical switch. I'm familiar with these. I see these at my work all the time. They're good for similar types of photoelectric micro switches. They're great for homing robotics and all kinds of things, and basically used for homing the position of motors and whatnot. So I've seen these H-type slotted switches a lot. Not one quite like this though, but anyway, this is it right here. And so one side you've got a infrared light emitting diode. Well, actually you have two of them, anode and cathode on one side, and then you've got a photo transistor too on the other side. So you've got collector and emitter. Pretty neat. I actually tested this guy out of circuit, applying a bit of voltage, just a bit above the forward bias voltage for the infrared diode, and checked for continuity on the collector side or detector side, and it wasn't getting anything. So I think this guy, and I mean that would make sense because this guy again was stuck in the open position, or this switch was depressed, and it was stuck that way, and it still wasn't disabling enabling the high voltage. So this guy must be faulty. But I needed to figure out a little bit more about how this works. I still wasn't really quite understanding how, just by looking at it like this, you can kind of see through that here. See, when you depress it? Well, how is that letting infrared light pass through? You know? Is it letting one just pass through and the other one stays closed or open? I needed to take this thing apart. And in fact, you can kind of, it wasn't apparent to me at first, but this this is not all one component. This guy in the center here is that component in the datasheet, but this is just some additional actuator that they've actually glued it in place. So I needed to get this thing out to take a closer look, and just give me one sec. Sorry about that. And so this is this guy removed. And now it makes perfect sense. So now when you depress this guy, the little holes match up with the slots where the infrared light can pass through to the phototransistors. Okay, so pretty neat. I hadn't seen an actuator like this, so that wasn't clearly apparent to me. But that provided me all the information I needed to develop a way to bypass this guy. So this is what I came up with. Don't ask me why I put the LEDs here. I just thought infrared emitting diode, LED, close enough. But the most important part for these is the transistors. So I've got the base of these transistors tied in to these LEDs, which are just in series. Okay, so when voltage is applied to these LEDs, it'll apply to the base and it'll turn on both these transistors, which are just, their collectors and emitters are just matched up in the same position as to where the emitter and collector pins on that photoelectric switch or sensor are. That's what I came up with. And yeah, I'm going to see if it works. If it does, awesome. And if not, we'll have to figure out something else. But, yep, let's test it out.
Living community by visiting thequadrangleccrc.com.
We live in stressful times through tailored wealth management.
All right, here we go for the test.
Learn more at raymondjames.com. The John D. and Catherine T. MacArthur Foundation,
Nice.
recognizing exceptionally creative individuals. This year's MacArthur Fellows and more information
Works.
at macfound.org. And Subaru.
And the LEDs below look pretty cool.
Subaru Crosstrek Wilderness with off-road capability and 9.3.
Someone who got into big trouble because they used an app. Our panelists are going to tell you about this. Pick the one who is telling the truth and win the waiter of your choice of your voicemail. You ready to play?
I'm ready.
All right. First, let's hear from Adam Burke. At first, Marcus Jennings was thrilled to participate in the beta test of a new communications app called Sure, Mom. The idea is the app creates a realistic AI audio.
Alright, so I've got a resistor hooked up to this guy. Okay, on the left side of the test fixture, and we're gonna see if we can get a curve up on the screen for this guy. So for a resistor, it's not a semiconductor, but so we should be seeing a linear line on the screen. It should just be a good representation of Ohm's law. So let's give that a try. So we're gonna switch it to the left, and nothing happened because the variable collector supply is off. But so we do see a line going like that, and by adjusting the vertical, you can see the change in the slope. Same with the horizontal, so that's a good sign now. Let's see. What's interesting is we should just be seeing a completely straight line here. That shouldn't be. So that's interesting, but showing some signs of life, so that's a good sign. Yeah, so, you know, I'm a little bit curious as to why it's got these little, you know, what's going on there. Oh, interesting. Oh, okay. That's odd. Oh, yep. Something's not happy. Oh, okay. That's interesting. All right. So that's a resistor, and obviously there's definitely, this thing is still has some issues that we need to figure out. But yeah, okay. Let's try a diode next, see what happens. Okay, so I was messing with this guy a bit earlier, and I was able to get traces for a diode, and even a Zener diode that looked normal, but now, you know, the zero function works, but as soon as I let go of that, the trace just goes right off the screen, so something odd is going on now. For AC, that's normal, that should be there, but yeah, so something strange is going on here. Not sure what the problem is. Now see, there, it returned to normal. But, you know, see, now it's looking, we still have the resistor connected to it. But there's still, like, something still isn't quite right. Yeah. Alright, so, let me try hooking up a diode again, see if I can get it on camera. We'll just leave the camera on while I do this. Okay, so this is just a 1N4937, so this is just a standard diode. Nothing too special about these. So let's just see if we can get at least a nice curve. Okay, so that is what you'd expect. Okay. So this is the reverse bias voltage. So you know you've reached that, and so that is normal for a diode. Now it's still doing that little curvy thing down there, which is a bit odd. And obviously we saw it all jumping all over the screen earlier, which, you know, and see, you shouldn't be seeing these two lines like that. You know, let's adjust the max. So that's the max power. Yeah, see that? We shouldn't be seeing this line going up, okay? So that's odd. Yeah, that's not supposed to be like that. That looks a bit more normal, but not, this guy shouldn't be shooting upwards like that. So, yeah. You know, it's almost like there's some sort of weird looping going on. And this is the looping compensation. So you'll see that when you're looking at much lower, when you zoom in and you're looking at much lower current per division. But not, I don't believe you should be seeing this at this setting. And again, look, I'm still learning how to use this, but yeah. Let's see what happens when we invert it. Oop, sorry. Yeah. Yeah. Yep, so this is just the reverse breakdown voltage. So that's normal. I mean, reverse bias is what I mean. And so you're not seeing anything. It's still not letting any, it's not breaking down. So that is still what you'd, but you know, it should just be a straight line. You shouldn't see this line coming off there like that. So not sure what that's about. But it's somewhat functional. Okay. And then let's see if we can. And see, this is an AC, so you're seeing both. You're seeing both the reverse, the forward voltage, and reverse. Okay. And so what we can do actually is put a Zener diode on here next, and then you'd see the Zener voltage on this end. But this is just a regular diode, so you're not going to see that. This looks normal. This is what you should see. So let's give that a try. I'm just going to keep the camera on while I do this, just so you can catch any funky things going on. But let's do that. And now it's looking, see again, it's looking a bit more normal now. I don't know if it just needed some time to warm up or what, but yeah. And yeah, yep. So let's pull out a Zener diode. Okay, let me see if I can find one here. This is a 1N5343. So this, I believe, is a 7 0.5 volt Zener diode. And so we should see a in AC mode we should see the forward voltage, and then on this side of the screen the Zener Zener breakdown voltage, or Zener voltage, I'm sorry. Okay, so now we're not, I did apply voltage to the left side of the test fixture, but you're not seeing anything because the collector voltage is at 0. So let's bring that up, and yep, so you can just barely see that. But yep. So you see, that is this is a great example of a, an IV curve for a Zener diode. So you've got the, I just moved it a little bit over to center, away from center, but this is the forward bias voltage. So this would be at about 0.7 volts, and then this should be at roughly 7-8 volts, the Zener voltage. So let's move it back to the center. Now, let's see here. Let's adjust the horizontal to see. So this is at 5 volts per division, so this looks about right. I still got to figure out how to use this instrument, and we don't even know if these controls are working properly, but at 5 volts per division, that's looks to be roughly about 7.5, 8. The forward bias, however, that should be a little bit closer to the center. But again, I gotta look into more and how to use this instrument. So if we go in the opposite direction and it decrease the volts per division. So this is at 1 volt, and you can see it didn't change at all in 1 volt. So this is 2, 1. You would think this would, for example, at 2 volts, this would be closer to the center, because this should be about like I was saying, just 0.7, 0.8 volts, somewhere right below 1 volt. So at 1 volt per division, this kind of makes sense. And let's even go to 500. Yeah, see, this looks normal. So at 500, this is at 500 millivolts per division. So you can see this is 500 millivolts. This would be 1 volt. So this is about right. But it's interesting that, it doesn't really change much between 1 and 2 volts. I don't know if that's intrinsic of the instrument, or that there's a problem with it or what, but I'll have to look into that more closely, just something I'll have to notate. But yeah, so this is good for, it's looking like a Zener. Is it accurate? Not sure yet, but at least we're seeing that, that characteristic curve for a Zener diode. Now, let's go back to the NPN. Okay. So this would just be showing the forward bias voltage. Okay, so let's, if we come back down, now again, you're still seeing that looping going on, which shouldn't be like that, but this is just the forward bias. And if we go to PNP, so if we reverse bias the diode, and And see, now we're just seeing that's the Zener voltage again. So we're just, AC, you get to see both of those flavors, and then this is just the PNP, just the Zener voltage, the reverse bias. So this is promising, I'll say. Now let's try a transistor and see what happens. So just give me a second here while I dig up a transistor, and I need an additional lead. Okay. Alright, so it took me a while to find an NPN transistor, but there it is, hooked up haphazardly like that. But let's see if we can get some steps and see if we can get a curve for a transistor. We should let's see. Step generator. Now, increasing the amplitude, we should see this getting larger. And it's not. Okay. So that's not a good sign. This rate button is stuck. Let's try just twice see if that. Yeah. So we aren't getting anything there. No. So by increasing the number of steps, we should be seeing this. You should be seeing multiple curves appear on the screen. That's not happening. Multiple traces appearing on the screen. So that's not happening. Yeah. Didn't have the step family on button pressed, so maybe. But yeah, no. See? Still nothing. So yeah, it looks like we might have a problem here with the step generator. It may not be working. Yep. Or maybe there's no voltage being applied to the base. But still, that would be yeah, I'm not sure. Oh, I didn't even have the voltage applied to. I didn't have the test fixtures on, so let's try that again, but yeah, still nothing. So, might have a problem with the step generator. Alright, well, I am in a different change of scenery here. I decided to bring the curve tracer to my work, which, you know, gives me a little bit more room to move around. I mean, I got a small place where I live and don't even really have a dedicated area to work on stuff like this. And I mean, it's one thing to work on smaller pieces of equipment that don't have as high voltages there, but just for something like this, I wanted to bring it to the lab. So, yep, so that's the reason for that. And I didn't mention this before, but this thing is not meant to be moved, all right? I mean, it is heavy. I was not expecting it to be that heavy, but I should have known better. I mean, this thing must weigh close to 50 pounds, maybe. I mean, it is really heavy. Definitely not meant to be carried up and down 3 to 4 flights of stairs. I live on the 3rd floor at home, so yeah, I think this is where it's gonna stay for a bit. But you know, I did want to so I moved on and did check some of the power supply voltages, because I mentioned earlier this thing's definitely got some issues that we'll need to take a look at. You know, step generator doesn't seem to work. Another thing that I noticed is the cow button. When you press it, it just, so right now it's in PNP mode, and you know, let's see, when you press the cow button, you should have it display offset set to 10x, depending if you're doing horizontal or vertical, but it shouldn't disappear off the screen like it is now, the trace. Okay, it might change position, but it's not going to just disappear off the screen. So that's one thing. Another thing that I found that is problematic. And again, the step generator, as I mentioned before, also we noticed on the trace when we were testing the you know, the resistor and the diodes, it looks like there's some looping going on or some weird deflection. So this thing definitely needs some work done. And first thing that you start with, testing voltages. Now there are a few voltages you can test. This is the low voltage regulator board, quote unquote low. Voltages on here are as high as 100 volts. In fact, that's actually what I'm got my test leads on now. And you can see on my meter, we're reading 91 volts. So what's interesting is actually at home, it was much lower. It was like closer to 80. I don't know if that's just a difference in the line voltage between here and home or what, but still, this is actually well out of spec for what the manual claims. And I have those here. So for 100 volts, let's see, yeah, plus or minus 2.5 volts. Okay, so yeah, definitely out of spec. And for all the other ones, they were low as well. You know, there's a minus 75 here, plus 12.5, minus 12.5, 4.5, 5 volts. All of them are out of spec and reading lower than they should be. Another thing is there's, for the minus 75, you have a trimmer capacitor right there. That I turned all the way as far as it can go, and I'm still only getting minus 65. So definitely have some problems with the power supply. Probably is due to some bad caps. So what I'm going to do next is hook this guy up to my oscilloscope and see if we can see any ripple. Alright, so now I've got my oscilloscope probe hooked up to this guy, and quick note, so the curve tracer right now is hooked up to my isolation transformer, which is also a variable power supply But if you are going to be, if you're watching this video because you want to do something like this and you're not familiar with using the oscilloscope, you do have the potential to cause serious damage to you or the oscilloscope if you're not probing correctly. So by isolating this from earth ground, you really decrease the potential for that to happen. So it really gives me the ability to kind of probe wherever I'd like, much more safely. So just wanted to keep that, just wanted to put that out there real quick. But anyway, yeah, so right now, again, just like before, we are, M is ground and E is the 100 volt rail. And check out the scope. So same with the meter, we're reading 91 volts RMS, but look at that ripple there. Yeah, peak to peak, almost 6 volts, and of course we've got that characteristic 120 hertz. So this is definitely what you would see right after a full wave rectification. And what it's telling me is it's likely that we have some bad electrolytic capacitors, the filter caps somewhere. Now, this is pretty much the same for all of the voltages, and just like the accuracy for the voltage, there is also a spec for the ripple or noise that you should be seeing. And again, for 100 volts, the manual allows 20 millivolts of line frequency ripple. We are well above that at almost 6 volts. So, that is a good indication that we have some bad caps. Now, time for the fun part. So, these caps aren't these on the board here. Now, I actually looked at those, and they're not. I didn't pull them out of circuit or anything, just with my ESR or LCR meter. They didn't test all that bad. The caps that we're interested in are actually behind these boards. You can see one of them back there. That's a C791, I believe, and it's going to be a pain to get those out. But it's going to have to be done. This is what I got this thing for this kind of restoration. It's just, I'm excited to do it. It's just a little bit daunting because, it's not like an OR piece of equipment where you just have one nice Molex connector with all these. I mean, look at all these individual connections that I am going to have to keep track of. In fact, I'm probably going to just label each one of them. I know the manual's probably, it's going to tell you what color wire goes where and whatnot, but I just want to make it maybe a little bit easier on myself and just put a piece of tape on each one of these and label it, just to make it easier if I'm going to do this. But yeah, we're going to have to get these boards out potentially and get these caps, which are probably sticking out on the other side. We might have to remove the CRT. I am not sure. But yeah, that's what we've got ahead of us. Yeah. Just wanted to show you guys one more thing. So right now I've actually got the oscilloscope hooked up to the collector supply voltage, and it's set to in DC mode, which is also the anti-loop mode, so you don't get much of that looping at the lower when you zoom in at lower current per divisions. But yeah, so when you're in normal mode, it's a fully rectified sine wave. So check this out. It's still an NPN, which is positive, but look at that. There is no ripple on that supply. We're getting roughly 17 volts RMS, so a little bit above the 15. I'm not too worried about that. I also have to check the manual to see if there's a spec for this collector supply as well. But much different situation than the other supply voltages. So if we put it in normal mode, that's your fully rectified sine wave, and then PNP, it flips the sine wave. So yeah, and then you can even put it in, if we put it into AC, there you go. So not really seeing any issues there with the collector supply. So that's good. I'm glad to see that. And the collector supply voltage is a completely different source than those voltages we were checking earlier. It's a different transformer, you know, so it's a completely different circuit. So, but it's good that this is looking a lot better. Now let's check the high voltages as well. And now we're at the 350 volt range, so I have it set to the DC setting on PNP, so you've got roughly negative 370 volts. So if we flip that, brings it up, positive, and again, it's looking very clean. We go to back to normal mode. So you got your rectified. And then AC. So again, looking at the collector supply, it's looking really good. Don't really have the capabilities to test that 1500 volt setting, but I would like to get myself another high voltage differential probe so I could get up a little bit higher to test that, and maybe a high voltage probe, you know, that I could hook up to my multimeter. Don't have either of those. So, but yeah, let's turn that off for now. And so, yeah, I mean, I think we're going to leave that there. So next steps are going to be to get to those big caps that are, you know, you could probably see them on this side. Take that panel off. And gonna have to replace those, and then also gonna have to troubleshoot that step generator board and amplifier. But you know, those are the things that I know are definitely wrong. Probably discover more as I learn more about the instrument, but that's what I'm going to be tackling next, and we'll just, you know, figure out more as I go along. All right. Catch you guys next time.